Assalamualaikum warahmatullahi wabarakatuh, and very good day to everyone. So today we will look at next chapter in our courses, which is chapter 3 that we discuss on numerical in CFD, and we focus on pressure velocity coupling in steady flow. So in this chapter we will cover several topics. We start with the staggered grid. We understand what is the staggered grid. We'll look at after this, and then we look at the simple algorithm. The simple is stand for semi implicit method for pressure link equation. Okay, this one is the simple algorithm, and then they have extension of the simple algorithm. We call it a simpler. That's the simple revise. So they call it a simpler, and then another simple method that modified to improve both simple and simpler. We call it a simple consistent. Okay, then we move to another algorithm. We call it a Piso algorithm. Piso, which is stand for pressure implicit with splitting operation. Okay, something like that. Okay, so we look at one by one all this thing, and then at the end of this chapter we look at one of the example how the simple algorithm work to solve the problem or to solve the momentum and pressure equation in CFD. Okay, so as an introduction, maybe we need to recall back what we did in previous chapter. As we know that the conversion of a scalar variable, which is this one, is depend on the magnitude and direction of the local velocity field. And to develop our method in previous chapter, basically we assume that the velocity field was somehow known, but in general the velocity field is not known and emerge as a part of our solution process along with all the others flow variable. So in this chapter we will look at the most popular strategy for computing the entire flow field. And the transport equation for velocity component momentum equation can be derived from the transport equation, as we always find it in previous chapter, the transport equation. And every velocity component appear in momentum equation. So the velocity field must also satisfied with the continuity equation. That's the basic that we already learned in previous chapter. So for this courses we move to the simple flow, which is the two-dimensional laminar steady flow, and this can be clearly shown in the equation of two laminar steady flow as this one is momentum equation, and then this one is the continuity equation. This one is x momentum equation. This one is y momentum equation, and this one is the continuity equation. And if we look at from all these three equation, the pressure gradient term, you can see the pressure gradient, this pressure gradient term, which form the main momentum source term, or it must follow in general process. So this one is the momentum source. So you look at here, the pressure gradient is form the main momentum source in this flow field, and then with the solution of this equation set, which is this three equation, we have the new problem occur with this new set of this question. Okay, firstly, I said that two new problem, but this one have four. I write down here four. Okay, never mind. Okay, firstly is x derivative in equation. Sorry, in equation this one we have this x derivative. We have rho u or write down here rho u squared. All these equations is coupled because every velocity component appear in the momentum equation and continuity equation. So when all these equations are intrinsically coupled because every velocity component appear in this momentum equation, the most complex issue to resolve is the role played by the pressure. So by the pressure, and it's appear both in momentum equation. Okay, it's in both momentum equation, but this will not transport equation for pressure. There's no transport equation for pressure. Okay, so if we know the pressure gradient, which is that if we know this one, the process to obtain discretize for the velocity from momentum equation is similar that we did in previous chapter. However, in the flow computation, we also wish to calculate the pressure field, which is that part of the solution, mostly part of the solution of CFD calculation, and the gradient is not normally known beforehand. So we do not know the pressure gradient before we start to do some calculation in CFD. And another thing, for the incompressible flow, the density is constant, so that by definition not linked to pressure. Basically, another way to obtain the pressure gradient, the P, is through the equation of state, which is that P is the function of P, rho, and T. But in incompressible flow, the density is constant, so the definition is not linked to the pressure. So we cannot determine the pressure by using the equation of state. And the problem is coupling between the pressure and velocity introduces a constraint. The coupling between pressure and velocity, they introduce a new constraint in the solution of the flow field, which is that the pressure field is applied in momentum equation. The resulting velocity field should satisfy the continuity equation. Both equations should satisfy with the continuity equation. And then both the problem basically associate with the non-linearity in equation set. And then here the pressure velocity link can be resolved by adopting the iteration strategies such as simple algorithm method that introduced by Patanka and Spalding. And I think this one is quite familiar name when you study the CFD. And in this algorithm, in simple algorithm that we will look at after this, the Gaussian flux per unit mass F through the phasor I evaluate using the so-called gas velocity component. Since we do not know the pressure, so we do not know the convective flux at the cell, so we guess the value first before we do the simulation. So for the iteration process, we start the guess value of velocity and pressure, and then the process will iterate until the converge, and then until find out the guess value is nearly the correct value. The guess value is approaching the real value. So this simulation will converge for this kind. Okay, and then this one, the main features of simple is to enhance the guess value that we use to solve the pressure and velocity link equation for the momentum and velocity equation. Before we go for the simple algorithm, we need to familiar with the staggered grid first. Okay, basically the solution procedure for the transport equation or general properties, the transport properties equation, this one is developed in previous chapter, and of course to solve the momentum equation. However, not completely straightforward, since there are problems associated with the pressure source term of the momentum equation that needs special treatment, as we see from the previous equation. We have the pressure gradient dp over dx is the one of the source term in pressure in momentum equation. So finite volume method, as we discuss the rest of the chapter, it always discretize the flow domain and the relevant transport equation that equation, which equation, this question 11, 12, 13. 11, sorry, this one is 11 to 13. So, this may a correction there. So we need to decide where to store the velocity first. We guess the velocity, and then we need to define where to store the velocity. So we assume if the velocity pressure both define the node and the if the velocity and pressure are both defined at the node, this one, let's say the velocity and pressure is defined at this node, the point that we want to study, and ordinary control volume, this control volume, a highly non-uniform pressure field can act like uniform field in the time momentum equation. So let's say we have somehow checkerboard pressure field here, this one. So at pressure at this phase, this east phase, and the west phase, the small west phase, can be obtained by linear interpolation, which is that okay, I can write down here, which is that dp over dx is equal to pe, this one, minus p in the west divided by 2 delta x, because this one is delta x, 2 delta x, similar, and then this one also we can write down pe to pe, this one, minus sorry, this one, okay, not 2 here, because from here to here is del x, okay, so only del x, not 2. So this one we can use the similar for PE, this one, minus PE over 2. This one is divide by 2 here, minus this one divided by 2, similar this west phase. So we can simplify this one with this equation, which is that we have dp over dx is equal to pe here. We can use the red one. P is here and P west here over this one is delta x. So this one is distance, this one to this one is 2 delta x. Similar for in this direction, in y direction. So we have dp over dy. dp over dy is pn here, where it's lost here. Okay, north minus south there. Okay, so if you can see both in this equation 314 and 315, the pressure of center node is not appear here. This one, the pressure here is not appear in both equation. So we can substitute the appropriate value from the check prop, the value from this the checkboard pressure into this equation, and discretized gradient also 0 to all the node point, because we see here at all the point here, this cancelling each other, PE and PW, and also if you look at point here to here, so they cancel each other, so that we have the discrete zero gradient are zero at all node point. As a result, the pressure field will be the zero momentum source in the discrete equation as uniform pressure field. So if the velocity are defined as scalar node, the influence of pressure is not properly represented in the discrete momentum equation. So better we go to use the grid. To solve this one, we use the stagger grid for velocity component. This grid was introduced by Harlow and Welsh in 1975, 1965, something like that. So the idea for this stagger grid is to evaluate the scalar variables such as pressure, density, temperature at ordinary node point, but to calculate the velocity component on stagger grid centered around phase cell. So the arrangement of two-dimensional flow calculation show in this table, in this figure, and the scalar variable include the pressure stored in the node marked as this one. So the scalar variable stored in here, in this point. The velocity are defined as scalars phase set in between the node and are indicated by arrow. So this one is the arrow that indicate the velocity. This one is for velocity in x direction, not by u, and this one the v velocity, which is the velocity in vertical direction. And the u velocity are stored in the scalar surface. The u velocity stored here and here, and the v velocity are stored in here and in here for this nodal point. Okay, for the moment we continue with we can use with the original east. Where is the east? Okay, the original direction is west, north, and south. Here the u velocity are stored at the scalar facet. The velocity at different in three, of course in three-dimensional we have another faces in top and bottom. And in the stagger grid, the pressure not coincide with the cell facing u control volume. The pressure gradient dpdx is given, so it's given by the pressure gradient, given by this one for pressure gradient in x and y. And if we consider checkbox that this one, the pressure field again substitute an approach model pressure value in equation 316 and 317, yet a very significant non-zero pressure gradient term. So this one we have non-zero pressure term. The segregation can. Okay, so since this one we do not need to interpolation to calculate the velocity at the scalar field, scalar surface. So this one is the what we call the important thing, or why we use the stagger grid to calculate the pressure and velocity term for the momentum equation from the previous equation 11, 12 and 13. So it's just introduction on how we use the stagger grid, and we move to the momentum equation, which is that how I want to show to you. Okay, I use this one. You can refer to the slide for the rest, but I need this picture, this figure to explain the rest of this momentum equation. Okay, for the momentum equation, since the velocity is staggered, the new notation based on grid line and surface numbering will be used. So refer to this figure, to this figure. Unbroken line are numbered by mean of capital letter. So this one, this unbroken line, this line number by mean of capital. See how I want to explain. Okay, you see here, where is here? Okay, we see we have in x direction. So let's say in x direction, this one, in x direction and unbroken line. Okay, so this one represent the numbering is in capital letter. So you see in addition, this one is I minus 1 J, also J capital letter. This one is IJ capital letter, and this one is I plus 1 J, also in capital letter. Similar in Y direction, in the unbroken line, we have this one also represent the capital letter. This one is capital letter, and this one both are capital letter. And the dashed line is the construct surface are denoted by lowercase letter. This one is dot line. Okay, see here, this one is in x direction. We have what you call lowercase letter here. Similar here, we have lowercase letter, and also in y direction, in vertical line, we have J here. We have J small capital letter here. Subscript system, this subscript system IJ based on numbering will allow us to define the location of grid node and cell face with more precision. And scalar node located in the intersection of two grid lines are identified by two capital letter at point P, which is let's say here represented by two capital letter I, J. So this one is basically the point where the nodal point that we want to determine, represented by I and J. For some reason, the store location for the velocity are combination of capital and lowercase. For example, let's say which one? Okay, this one. This is a combination of I and J. I small letter, J and capital letter. So to calculate this one, sometimes we can use either backward or forward stagger grid. But for this figure, basically it's refer to the backward stagger grid, because if you see the I location, where is I location? Okay, this one is I location. For U velocity, this one is U, I, Uij. Okay, Uij is a distance minus from this point. So this point is minus half of, or minus delta x over 2. So this one is backward staggered grid I use because of this one. Similar, if you see in y direction also, we have the small, where is the small, this one is backward from the center. So from here we can express the new coordinate system, that discretized U momentum equation, and also V momentum equation, which is a momentum equation in x and y direction with this equation. Okay, so this one is the new notation, new coordinate system to discretize your momentum equation U in x and y direction. So from the new new coordinate system, let me refer to this figure. The new numbering system with east, west, north and south is one for the U control volume. U control volume involves summation of where's the summation of all the neighborhood, which is that we can solve using this one we can solve using the differential method that we look at previously. Differential method, either upwind scheme or hybrid scheme, and other method that's suitable for conversion diffusion problem. Similar for okay, this one they explain about y1. The coefficient contain combination of convection flux F and the diffusion conductance at U control volume phase, and then for all the phase convection and diffusion term, they can use this one by one at each phase cell, like this one. So what I can say here, the diffusion, the convection at the west phase, this the convection at here, sorry, where is the phase, where is the west? Okay, the point here, the convection at here can be written in this form, and here at this one, this form, this one, and this one, south and north phase color, this one. And also for the diffusion term, which is at D in west, D east, south north, written in this formula from this equation. So we write down all the convection and diffusion term in each phases of this control volume as all this thing. This one is in the x direction, and for the y direction, which is that V momentum equation, the similar thing we use, and at the end we simplified all the equation in this form. This one for the diffusion term, and the given pressure field description can be written volume. Okay, so if the pressure field is correct resulting velocity field satisfy control, as the pressure field unknown, we need to method for the calculating pressure. Okay, from all these things, basically we do not have the value for the pressure, but we need to link, we have value for velocity. We need to link the velocity and pressure to obtain the pressure. So that's one, we have to use what we call the simple algorithm to link between the pressure and velocity. That's why they call it the simple algorithm is the semi-implicit method for pressure link equation, which is that we want to link the pressure with the rest of the equation. And to initiate the simple calculation process, P, where is P? We guess the pressure, the P first, and the systematic equation in the equation 18 and 20 are solved by using the gas pressure field, yield, the velocity component U and V as follow. Okay, so we have this one from this equation, panjang, so equation 318 and 320. So we substitute the gas value. We can have this one also. This one is gas, P is gas value. So we also need to gas value for U and V here. So the P, difference between the P prime, the P equal to P star plus P prime, and then if you substitute all this thing into this equation, see that P here, this one meaning that P here is, from here we have P star equal to P minus P prime. So this one, we extend this equation into this one. To both equation for momentum equation, and also for the, we substitute this into equation, and then we can simplify as this equation. We reduce or we omit this term, and we have this kind of equation for U gas and V gas, where this one is simplified from this equation. And the rest, similar thing. I don't need to explain a lot here, but the most important thing is, okay, this one they use the scalar thing, the method that we already applied in the staggered grid to obtain the value for each phase of this control volume. So all this thing with a lot of notation I and J here, you can simplify, and at the end we can write down the Aij, which is this one, A here, the properties here in term n is coefficient as this equation. So what we can simplify from all the lot of equation I, J, capital letter, small letter, everyone, for the simple algorithm is how to this simple algorithm work. So we can simplify as in this flowchart, which is that start here, we guess the initial value for the properties that we want to study. Let's say for pressure, for U component, for the V component, and also for the transport properties. We guess the value and then solve the discretized momentum equation by using the guess value. So from here we got the value for this one, and then step number 2, we solve the pressure correction equation, or the pressure that or the equation that we already show in previous slide, and then from there we obtain the pressure prime here, and that's time locate. We use the correct pressure for the velocity, which is that P is equal to P star P gas plus P prime. So when we have this one, we can obtain the pressure similar also when we have the U from here. We can obtain the correct value of U here. So from here we got the real value, the correct value of pressure and all the properties. So we solve all this transport equation by using the correct value of pressure, velocity in direction, and also velocity in y direction. At the end, we can obtain the value, the correct value of the transport equation that we want to study, whatever lah, temperature or whatever, and then we check the converge. If did not converge, meaning that maybe a certain value from the gas value is not correct, so we need to set back the gas value, start again from here, and then go through the process until the solution is converged, and then stop. That's how the simple method or simple algorithm work, which is that start with the inertial gas. So that's all for simple method, and after this we look at the rest of other algorithm, which is the simpler, and also the PISO. So thank you very much. See you again in next video or next class.